All right, good afternoon, everyone. I'm delighted to see so many of you this afternoon for the colloquio of the Classe di Scienze by Professor Alfio Quarteroni of the Politecnico of Milan. Alfio does not need a lengthy introduction. He's universally recognized as one of the leading applied mathematicians of our time. He has made fundamental contributions to the analysis of partial differential equations, numerical analysis of partial differential equations, and modeling and applications ranging from cardiovascular modeling to different parts of engineering, including geophysics, improvement of sports performance. Is also well known for leading the team that organized the calculations, the optimization of performance for the Alinghi yacht, the boat that won 2 editions of the America's Cup in 2003 and 2007. Alfio has numerous honors. Well, let me start by saying that he is currently professor of numerical analysis at the Politecnico in Milan, has been director of the chair of modeling and scientific computing at EPFL, Lausanne, from 1998 until 2017, and previously has also been professor of mathematics at the University of Minnesota in Minneapolis. He's a member of the Accademia Nazionale dei Lincei, European Academy of Science, Accademia Europea, and the Lisbon Academy of Sciences. He's the founder and first director of MOX, the Modeling and Scientific Computing Group at the Politecnico of Milan, and of Mathixe at EPFL, Lausanne, co-founder and president of MOXoff, which is a spin-off company in Milan. He's authored 25 books, is editor of 5 more books, author of several hundred publications, editor of a large number of scientific journals, and editor-in-chief of 2 book series published by Springer. He has been invited as a plenary speaker in more than 300 conferences, has been in particular twice invited at the International Congress of Mathematicians, 2002 in Beijing, and again as a plenary speaker in 2006 in Madrid. He has many awards, like I said, including the Ghislieri Prize, International Galileo Galilei Prize for Sciences, 2015, and the Euler Lecture, 2017 in Berlin. And he has received 2 advanced ERC grants, MathCard in 2006 and iHeart in 2017. We'll probably hear something about that today. And numerous others, grants and awards. I should mention he was recipient of the Galilean Chair from the Scuola Normale Superiore here in 2001. He's Doctor Honoris Causa in Naval Engineering at the University of Trieste, and he's a Science Fellow of the first class, and so on and so forth. So, with that, I'm going to leave the ground to Alfio. Thank you for being here.
So thank you very much. Great pleasure and honor to be back at Scuola Normale, and thank you, Michele, for this very generous introduction. So I will talk on this specific topic, which is the modeling of the cardiac function. Well, let me first of all acknowledge that there are many people who are actually doing the work, most of the work, and they are coming from Lausanne and Milano and a few other places. When I started long ago with this type of topic, well, first of all, it started because of the specific request made by a medical doctor, a young medical doctor who was coming back from United States, where he was used to operate and make a heart replacement, and went back to Italy. He was then going to the classical routine, and so I was a bit disappointed. So he came and he wanted to know a bit more about the physics or the physiology using quantitative methods. So this was the way I started long ago, and we started with this type of work actually. So this represents one of the main arteries that we have in our body. We have very many arteries, and this is called the carotid artery, and we have it in our neck. We have two of them, one on the right and one on the left, and there is a main branch, which is this one, and then you have a bifurcation. One is the so-called internal carotid artery bifurcation, and it brings blood directly to the brain. So this is an healthy carotid artery, and what you see here is the fluid and structure interaction. You see the fluid, which is the blood flow, and the colors refer to the intensity of the velocity field, right? So Vx squared plus Vy squared plus Vz squared. And the colors are red for the highest value on the scale and blue for the lowest value on the scale. And then you see the vectors. And this, say, pink area is the one of the artery. So this is the material part of the story. And what you see here is the interaction between the fluid flow and the deformation of the solid part, which is the mechanical wall. So mathematically speaking, this is, say, a couple PD problem where you have from one side the Navier-Stokes equations. So this is too light, I hope you see it. Those are the Navier-Stokes equations, which are there to represent the behavior of the dynamics of blood. You can perhaps recognize the first equation, which is the momentum equation, conservation of momentum. The second equation, which is the conservation of mass. So UF is the velocity of the fluid. Fluid means blood in this case. P is the pressure. And so those are the classical Navier-Stokes equations. The only difference with respect to the classical form, classical Eulerian form, is that you see these red terms, and those are there because we are actually operating in a domain which is moving on time. So the computational domain, the domain of the PDE, is the lumen of the artery. And the lumen of the artery is changing in time because of the deformation. So this W accounts for this deformation. W is the rate of deformation of the internal domain, say. And this derivative is not the Eulerian derivative, it's called ALE derivative, arbitrary Lagrangian Eulerian derivative. Well, this is a bit technical, but the point is that when you use PDEs to solve a continuum problem in continuum mechanics, you typically use Eulerian form for fluids and Lagrangian form for solids. And there you have both fluids and solids, so you use a kind of intermediate representation, which is called ALE. And this explains why you have this extra term. But otherwise, you have the classical Navier-Stokes equations. Those are equations for the deformation of the solid, which is the wall, the vessel wall of our artery. So this is a hyperbolic equation with typically nonlinear constitutive laws. And on top of that, you have an extra equation, which you call simply geometry problem, because you want to be able to retrieve at each time the actual form of the lumen. The lumen is the part where you have blood flow, right? So you have a couple problem with three equations: Navier-Stokes, elastodynamics, and the Laplace equation, say. And of course, you have coupling conditions. And the coupling conditions occur at the interface between the fluid and the solid. And this is called the endothelium interface, the endothelium wall, physically speaking. And the coupling conditions are kinematic condition, meaning that the velocity, if you see a particle of fluid hitting the boundary, the interface, well, its velocity should be equal to the time derivative of the displacement of the wall. So it sticks there because of the viscosity, say. The second condition is the equilibration of the stresses, which means that the energy that is passed from the fluid to the wall is balanced by the energy that is returned from the wall to the fluid. And the third equation is an equation of adherence, say. You don't want to have any cavitation at the interface. So this is a coupled system. And the simulation that we have seen before is the numerical solution of this coupled system. So we'll say very little about numerical approximation in this call, in this seminar, even though this is a major part of this work. So of course there is no exact solution for those equations. You don't even have a theorem stating that under the actual forcing terms, these equations are well posed. So this is a big gap that we have in this development. So this is work in progress. But if you want to solve it numerically, you have to approximate. And you have to approximate it by, well, there are many different methods. Here we typically use finite element methods. But I will not insist on that because this will take for a long time, say. Now, the point is that when you have a solid, say, mathematical representation of your problem, and you have a good numerical solver for the problem, you can use it for many different types of applications. For instance, this is the aortic. This is the aorta, the main aorta. Heart is somewhere here. This is the ascending aorta. This is called the aortic arch. This is the thoracic aorta. This is the abdominal aorta. And those are arteries that then connect with the carotid that you have seen before. What you see here are 2 heartbeats. So this is a physical time. T goes from 0 to 1.7. These are 2 heartbeats. And we'll see later that heartbeat is made of 2 phases. One is the systolic phase, when our heart contracts, and then blood is ejected into the aorta, and then it reaches the 10 to the power 32 cells in our body. And then you have the diastolic phase. The diastolic phase is when the heart relaxes, and in particular, in that phase, the oxygenated blood coming from the lungs enter into the left heart. So here you see that. Now you see when this is more or less the end of the first heartbeat. Now you see starting the second heartbeat, where the heart contracts, and you see that everything becomes more red. And this is because the values of the pressure in this case increases. And what you see here are the blood particles. Sorry, the trajectories of the blood particles. So those are the streamlines. Though this is just a cross-section that we take at that level. And you see the rotation of the blood particles. And what you see here is the displacement of the vessel. So we go from 0 up to 4 millimeters, which is considered to be, mechanically speaking, a large displacement. The point here is that when you know how to solve the problem locally, let's say in a specific tract of the artery, you like to connect it with the rest of the circulation. Now, the rest of the circulation is made of hundreds of big arteries and thousands of small arteries and billions of capillaries. And you cannot pretend using Navier-Stokes equations and the elastodynamics equations everywhere. I mean, this does not make any sense. So you need to introduce a simplification. And the simplification here is this one. We want to use 3-dimensional analysis only in those compartments where we know that we are interested in 3D values or 3D quantities. Then we want to use 1-dimensional analysis for the most important arteries and veins. And at the capillaries, not even the 1-dimensional models are affordable. So we use the analogy with electrical circuits. So here we use ordinary differential equations. We only compute the evolution in time of average quantities. In 1D, we only compute the longitudinal velocities and the pressure. In 3D, we compute everything. So we call this geometric multiscale. Geometric multiscale because you have the interplay between 3D, 1D, and 0D differential equations. And of course, the point is how do you connect 3D with 1D and 1D with 0D mathematically. So this is an extra problem that you have to solve at the modeling level, say. Just a comment, because I don't want to insist with that. The 1D is based on the classical Euler equations. So Euler introduces famous Euler equations for gas dynamics, the ones that are still used today for designing new airplanes, for instance, for blood. At that time, Euler was professor in Basel, and he wanted to consider the fluid, blood, in a cylindrical vessel, deformable vessel. And today, in modern language, we would say that he started from Navier-Stokes equations coupled with elastodynamics, the monster system that I showed before, and by asymptotic analysis, by making other assumptions, you end up with a 1-dimensional model. But at that time, the Navier-Stokes equations were not available yet. So he derived this type of model as today we would do it by starting from Navier-Stokes equations. And we got the right equations. So those are nonlinear hyperbolic equations, actually system of nonlinear hyperbolic equations that we connect with the three-dimensional Navier-Stokes system coupled with the elastodynamic system that we've seen before. And with that, we can simulate the whole circulation in the whole body. So typically what you do is the following thing. We use as background model the one-dimensional model of Euler in any single artery. We have here about 100 arteries. Those are the most important arteries in our body. So we use Euler equations everywhere with suitable interface conditions. And then we use a three-dimensional model only in those parts where we actually want to see very detailed, in a very detailed manner, what is going on. So it's a kind of Lego. You put your three-dimensional piece in those positions where you actually want to see much better what's going on. All right. So I started with this type of remark because when we actually started, we are not able to attack the heart, say. So we start with external circulation. And of course, we use it in many different contexts. Today, we use many different, collaborations with doctors to address different type of pathological issues. But then, at a given point, we had to treat the modeling of the heart. So the heart is the main engine that we have and is at the very basis of what happens. So let me go back for a little while. Okay, maybe have it here. Okay, maybe have it here. So just for those who are completely unaware of what happens in our heart, we basically we can basically describe the activity of the heart in this way. We have venous blood that enters into the so-called right heart. So through the vena cava. This is the vena cava. And it enters in this right atrium, and then it passes through this valve, and it enters into the right ventricle. And then it's pumped through this pulmonary artery to the lungs. It gets oxygenated, and then it gets back to the left atrium. And then it goes into the left ventricle, passing through this mitral valve, and when this left ventricle squeezes, then the blood is ejected into the main aorta. And you see the simulation that I've seen before. So this is from a purely mechanical viewpoint. But why does the heart beat? What provokes the beating of the heart? Well, at every instant of our life, we have a spontaneous electrical signal that originates from this point. This is the so-called sinoatrial node. This is actually made of a bunch of natural pacemaker cells. They beat spontaneously, they create a signal. The signal propagates through the two atria, the right atria and the left atria, and then it goes to this other node, which is the atrioventricular node. It stands for a little while, allowing the atria to contract, and then it's propagated through this network of fibers. These are called the Purkinje fibers, through, you see, until the apex of the heart. And from there, it reaches all the possible cells in our myocardium, which is the muscle. So there is an electrical signal that propagates and creates, of course, an electric potential. And then, for a very complex mechanism at the cell level, you see that the proteins that are forming the cells, in particular the channels that separate the cell from the intracellular fluid and extracellular fluid, opens and close. They allow the ions of calcium and potassium to go back and forth. This polarizes and depolarizes the cell, and because of that, the cell contracts. So you can think that every single myofilament will contract and will relax. And that the aggregated action of all that creates the contraction and dilation of the heart. So when you see this, you see that there is, on top of the electrical field, there is the mechanical deformation of the heart, and you want to introduce a model to describe the mechanical deformation of the heart. And here you have two different effects. You have what is called the passive mechanics and the active mechanics. The passive mechanics is the standard reaction of an elastic structure to an external stimuli, and this is made complicated by the fact that in our heart we have fibers and collagen sheets. So it's a kind of smart material that we have to account for. So you need to develop the equation to introduce the equation for the myocardium, and moreover, you have the active component, the active behavior of the fiber. The active behavior because the fiber get excited electrically. So you have two components. You have the passive components and the active component that make the heart beating. So you need to model all this, and at the end of the day, what you end up with is a model that encompasses all those type of mechanisms. So let me try to explain now on this picture, which is a very simplified representation of the whole story, what we have in place. We have, say, a box where we write equations that describe the electric potential and the propagation of the electric field. Then you have a box that is there to describe the ionic activity at the cell level. So this is macroscopic, this is microscopic. Then you have the mechanical activation of every single cell with the deformation and the contraction and relaxation. Then you have the active and passive mechanics that occur at the global myocardium level. Again, this is macroscopic. And then you have the fluid dynamics in the four chambers, in the two atria and the two ventricles. You have the blood. And then you have, of course, the valves. We have 4 valves in our heart. And, of course, every single block is connected with the neighboring blocks by, say, transferring suitable quantities. Those are called the transmission conditions. So you see here the quantities that are, say, transferred from one block to the other. For instance, from the fluid dynamics and the active and passive mechanics, you have the deformation rate and velocity and the stresses. From the electrical potential and the active and passive mechanics, you have the deformation of the solid, and here you have the ionic current and the potential, and so on and so forth. And this is the, you see, when you study PDE, you start from saying, let omega be a domain in R2 or R3, right? So what is omega here? Omega here is the domain where we want to solve all those problems, and here you see you have the cavities, the 4 cavities, and this is omega F. You solve the fluid, the blood flow here. Then you have omega S and omega E. S because of the structure, myocardium. E because of the E stands for electricity. And this is the domain, the myocardium, where you solve the equations for the deformation and the equation for the electrical field. And then you have these leaflets, which are the valves, represent the valves. In those leaflets, you solve the model for the valve. So this is a kind of, say, schematic representation of the whole model. Now, in terms of equations, those are the equations. So this is what we call the integrated R model. So those are, say, partial differential equations and ordinary differential equations that are there to represent all those pieces of the puzzle, say. So those equations are time-dependent, nonlinear reaction diffusion equations, whose solution is the transmembrane potential, and the gating variables. Gating variables stand for, so these are binary quantity, which is 0 if the channel, the ionic channels are closed, and 1 if the ionic channels are open, and C is the concentration of different species, like potassium and calcium, say. This is a system of ordinary differential equations that describe the ionic activity. This is an ordinary differential equation that describes the rate of deformation of every single cell of myofilament. This is the system of elastodynamics. Of course, is a nonlinear system that allows for the description of the deformation of the myocardium. Those are the Navier-Stokes equations that you write in the left ventricle. And then, again, you have a model to describe the deformation, the dynamics of the valve. So this is the global system that you, in principle, should have to solve in the left ventricle. And then you have to replicate it in the left atrium, the right ventricle, and the right atrium. So you have 4 times this type of coupled system. And once you have it, you have to connect it with the external circulation. The external circulation goes from one side to the, say, to the lower limbs, and from the other side to and this is the global circulation, say, the systemic circulation, and from the other side to the lungs. So this is the global picture, right? Now, there are many different comments that you can make. First of all, you don't have any sound mathematical theory to decide whether or not this is a well-posed system, so you don't even know if there is a solution. Of course, we are living bodies, so a solution exists, right? It's also unique, hopefully for us. It's a multiscale system. It's a multiscale system because you have a multiscale behavior in space and time. In space, you go from the micron, which is the characteristic size of the cardiomyofilament, to the centimeters, which is the scale of the whole body, of the whole heart. And is a multiscale in time because the electric potential, the polarization, depolarization occurs in 10 to the power minus 4 seconds, while a heartbeat occurs in 1 second. So you have very different order of different scales for both the spatial variation of these quantities and time variation of these quantities. Of course, it's non-linear and everything is coupled, and this is what, in principle, you should be able to solve to have a complete description of the heart function. So the idea is to use this type of model to reproduce the functionality of the heart. Now, the very first point is when you want to solve a partial differential equation or a system of partial differential equations, you need data. Data mean the shape in this specific case, and of course all the quantities that are there to provide the boundary conditions, the initial conditions, and the coefficients of the model. So the shape means having the shape of a specific person available, and this is very difficult to obtain. I mean, by imaging, it's extremely difficult to reconstruct a complete heart from a real person. So this is a kind of fake, but indeed is not really fake. This is you see a CAD model. This is a real heart which has been segmented and reconstructed from a private company, and now is available. You just buy it, and you can use it as a starting point. So this is our benchmark for the time being. And then, of course, there's a lot of activity that regards patient-specific applications. So we start from this part, and of course, you need to start from there and try to solve your global system of PDEs. Now, as you can easily guess, there is no exact solution for that global system of PDEs, so you need to approximate it. When you approximate it, you need, first of all, to go from the infinite dimension to the finite dimension. This is always the case when we have partial differential equation to solve. What does that mean, going from the infinite dimension to the finite dimension? What it means to introduce, in particular, a system of representation of the variable, the velocity, the stresses, the potential, the ionic currents, and so on and so forth, in a discrete way. Discrete way means only a finite number of points, right? Maybe very many, but finite, because there is no computer yet which is capable of addressing an infinite dimensional problem. And here the points are obtained in this way. We introduce simple elementary shapes. In this case, those are tetrahedra that partition the domain. For instance, those tetrahedra provide a triangulation or partition of the left ventricle and of the left atrium. And you have the same for the myocardium. Those are independent partitions, say. And at the end of the day, what we'll have will be solutions of the problem of our PDE, called global system of PDEs, in, say, every vertex of this tetrahedra. Of course, the details are extremely important. We may think that our heart is made of 4 cavities with a very regular shape. Typically, the ventricles are represented by ellipsoidal forms, but in fact, inside, they are not empty. We have the papillary muscles and the trabeculae. They are there to help the valves to open and close, and you have to reproduce this type of shape. These are, you see, is a partition by triangles of those surfaces if you want to make sure that at the end we'll have a correct representation of the actual shape of the domain. So how many of those points, how many of those tetrahedra should we use? Well, of course, the more you use, the higher the accuracy of your solution. And here you see two different representations. One is very coarse with 800,000 elements, and this one is very fine with 22 million elements. Now, for every element, for every tetrahedra, you should expect to have at least 10 different values. The velocity, the stresses, the pressure, and so on and so forth. So when you see 22 million, you have to think of a system that is 220 millions of variables. And those are typical numbers, right? So at the end, we'll solve problems with several hundred of millions of variables. Okay? These are results already. This is the left atrium, where we are simulating the presence of two ectopic beats that are not physiological. You know that one of the problems that occur in the standard, say, cardiology are the arrhythmias or the, say, tachycardia or arrhythmia, or fibrillation in the worst possible case. So these are disturbances of the rhythm. You see one example here. Instead of having a single front that propagates, you have two ectopic beats that create colliding fronts. So those are the front of propagation of the potential field. And you have this type of what doctors call the 8 re-entry. You have re-entry waves. They call it 8 because they say they recognize a kind of 8 on this shape. So this is something that you can do, but just by, say, exploring possible scenarios with your mathematical model. You don't need to be intrusive and make any additional, say, clinical investigation. You just change the parameters of your model and you try to reproduce this type of events. This is a beating ventricle. This is the left ventricle, and we are assuming here that there has been an infarct for that specific patient. The infarct brings a scar in the material, and we have 3 different types of scars. One is small, is here. One is medium, and the other is large. And of course, a scar is a region where the conducibility, that conducibility is very low. Sometimes it's 0. This means that the wavefront follow a pattern which is not regular. So you have a part of the heart that contracts regularly and another part that will not contract at all. So the result is that the pumping function of our heart is severely reduced. And what you see here is that you can measure the loss of blood that is ejected into the main aorta, and you see this curve here is called, from the doctors, the PV loop. PV loop stands for pressure of the of blood in the ventricle versus the volume of the ventricle. And in a regular ventricle, in a healthy ventricle, this should be, the black one would be the standard PV loop. Take the large scar, this is the yellow curve, and in fact, when you see the distance between these straight lines, the vertical straight lines, this is called the stroke volume. So the stroke volume is the amount of blood that is injected into the main aorta. And what you see here is that when you have a severe scar, the stroke volume is reduced by, roughly speaking, 20-25%. So you can quantify those type of things that you'll never be able to see from medical imaging by numerical simulation. And you can explore different type of scenarios to see the way the blood is reacting. For instance, this is a very severe pathology. What you see here is what is called the LBBB, which is called left bundle branch block. There is one block of the fibers, Purkinje fiber, that is, one branch that is blocked. And of course, the heart reacts in this very strange way. This is sometimes called electrical chaos by the doctors. You see a pumping action of the heart that is completely out of control. The fluid dynamics, well, this is also a kind of surprise because actually in our heart, the fluid behaves in a very, complex and structured way. What you see here is an healthy heart. This is the left part of the heart. You have the left atrium and you have the left ventricle. you see the blood entering through the 4 pulmonary veins. This is the oxygenated heart that enters here through the 4 pulmonary veins. And then when this valve, which is called the mitral valve, opens, then it passes into the ventricle. Then the ventricle relaxes up to the point where this aortic valve opens up and the blood will be ejected. So you see here 5 seconds of real life, say, of real fluid dynamics in the left ventricle. We are using Navier-Stokes equations in a kind of transition regime between laminar and turbulent. So there is one debate about the fact that the blood in our heart, even in physiological conditions, is turbulent. This is not completely clear yet. There's not a complete evidence that the blood is actually turbulent. There is not enough time for the turbulence to fully develop because of the pulsatility of the heart, and not enough space because of the contraction and the relaxation. But the blood is in a permanent transition toward turbulence. Somehow is in a disturbed regime. So this means that in particular, when you have to solve it numerically, you have to account for models that are suitable to treat fully turbulent flows. So it's not very easy. And you have an idea here of what's going on. Those are the coherent structures that are formed. And you see you have micro structures that are formed and they are dissipated, of course, on a regular beat. Those are the valves. These are the aortic valve. This is the aortic valve, which is made of 3 leaflets. And of course, they open and close very, very quickly, very suddenly. And here we have, of course, to solve the problem of the interaction between the valve displacement, opening and closing, and the blood flow. A nice corollary of this result is that you can measure the age of the blood. Age of the blood means for how long a blood particle will stay trapped into the ventricle, for how long. And what you see here, when you color all those particles, you see that at least in physiological conditions, 3 heartbeats are enough to wash out completely the blood from the ventricle. And this is an important news because there is no room for blood to stagnate in the ventricle. This is very important because you want to prevent the formation of clotting, for instance, in the heart. That would be fatal. All right, that's a bit too technical, I think, and I would rather like to, yeah, that's a bit too technical. I want to avoid that. Let me see if I can instead allow me, if you don't mind, 2 minutes, because I'd like to avoid this, since we have so many people here who are not from the field, and I'd rather like to go and show you something that is perhaps of more general interest. Really sorry for that. Yeah. So let me, right. I'd like to make a comment on some difficulties that are inherent to the fact that here we are trying to model a problem for living organisms. So we are not here to solve a problem for, say, a boat or an airplane or a Formula 1 car, where if you are good enough, you can try to reproduce the solution with the accuracy that is requested by engineers or by the manufacturers, in the sense that you have a complete deterministic environment that you have to address. Here, even though we are using equations for continuum mechanics in a deterministic setting, there is a lot of variability that you want to account for. And let me just make a general comment without entering into the details to see the way we can account for this type of variability and uncertainty. So what is uncertainty? Well, there are many uncertain features when you try to address these type of problems. First of all, you need experimental measurements. If you want to compute the coefficients, the parameters, the boundary conditions, the initial conditions that should feed the model, especially if you want to address receiving. Now, when you have experiments, when you have measurements, you have errors. That's inevitable. And very often those experiments, those measurements are uncertain. You don't really know the accuracy that you have when you want to reproduce data that are essential then for the model. So we have different types of uncertainties. The first one is what's typically called the epistemic uncertainty. Either because of lack of knowledge. If you don't know what you need, you will not measure it, right? And there are so many things in this model that are difficult to highlight that sometimes you really have missing knowledge, missing information. Or you have experimental error. I could not measure it correctly. This is called epistemic uncertainty. And then you have aleatory uncertainty due to stochasticity. An individual reacts differently each time. This is a kind of intrinsic stochasticity. If you just make an experiment on yourself, you measure your pressure and you measure it in 2 different instants now and then in 1 minute. After 1 minute, you'll have different values. Sometimes different for up to the 10%. We are never the same, even though there is nothing specific that occurred from one measurement to the other. Right? You have a metabolic response, you have psychological condition that changes. So this is part of the stochasticity. And then you have variability between individuals. This is extrinsic. Every heart is different than everyone else's heart, for instance. So how do you account for that? This is just one example, very simple example. What you see here is what we call the biventricular heart. You see the 2 ventricles. This is an image from the top, the 2 ventricles. And we are solving the electromechanics problem. We want to see the way these ventricles will deform. In the model, everything is the same, unless for one single element. I will tell you in a little while what this single element is. And you see the way the 2 ventricles contract. These are the same time instants. So just take this last picture. And you see it macroscopically the way this differs from that one. Right? This is the displacement. We go on a scale from 0 to 1.6 centimeters. So a big displacement. So the only thing that changes here is just a tiny detail, the orientation of the fibers. So our heart is made of fibers. The fibers have a different orientation. They go from the epicardium to the endocardium. So the myocardium is our thick part of the heart, right? So the epicardium is the external membrane, and the endocardium is the internal membrane. Now, typically from the external membrane to the internal membrane, there is a variation of the orientation of the fibers of 120 degrees, a big change. But you don't know the way you go from the external orientation to the internal orientation. There is no way to compute it from medical images today. So you have to reconstruct it by algorithms, mathematical algorithms. So what we have been changing here from the top picture to the lower picture, upper picture, lower picture, is just a little 2 degrees in the orientation of the fibers. And you see the way the global system reacts. So this is to say that there is a lot of uncertainty in this business because of the fact that if you don't know exactly the values you have to use to feed your model, you may end up with something which is very different. Well, this is a picture that tries to summarize the way we see the uncertainty and we treat the uncertainty. You see on this diagram, you have 3 different axes: simulation, control, and uncertainty. Simulation is associated with the forward problem. As soon as you know everything, you use data, you have a model, you want to reproduce results. So input to output through a physical model, right? Control is when you have external devices that you want to put in your heart. For instance, you want to create a bypass, a coronary bypass. You have different type of ways to create a coronary bypass. You may introduce a stent, which is a metallic struct, and you want to optimize this type of intervention. So you have a control problem, an optimization problem. And of course, this is much more expensive than this one, because you have to solve at every iteration the same type of problem. And then you have the uncertainty. And you have two different types of uncertainty. You have the forward and the backward. What is the forward? Well, the forward, you assume that you have uncertainty representation of your data, and you want to see the way this uncertainty propagates into the solution. This is a forward uncertainty. The backward uncertainty is that you measure quantities, and you know that they're affected by an error, and you want to recover the data that have produced that type of quantity in a say probability space. So you go back with the system, and you want to go from solution to the data. Now, all those problems related to uncertainty are extremely difficult to solve, because at every time you really have to solve a big problem, which is the heart model, and you replicate it for many, many times. So I use this type of slogan: 1 week per 1 second. 1 week is the time, roughly speaking, that you need on one of the biggest supercomputer in Europe to reproduce 1 second of physical time. And this solved me the forward problem just once. And when you use control optimization or uncertainty models, you need to solve this problem many times, because you are in a loop of minimizing specific functionals. So you understand how important it is to try to reduce this time, computational time, if you really want to create a dialogue with doctors. You cannot pretend doctor to stick for so long before seeing the result, right? So this is why we have been developing models that we call reduced order models that allow us to compress all this simulation, and ideally to make it possible to solve them in real time. So this is a big challenge, but I want to explain you with this just type of cartoon the idea, the mathematical idea. Assume that you can collect simulations from many different individuals over the time. In Pisa, in Italy, everywhere in the world, right? Assume that you have in a club, in a consortium, and can reproduce the behavior of the heart for all those individuals. Of course, you need big supercomputers, right? Because of the complexity of the simulation. But then you store all this information, and then we have a newcomer at the hospital. Well, you try to solve the same type of model, PD model, this monster PD model, but on a subspace made of the solutions that you have been computing before for all those individuals. So assume that you have 100 characteristic individuals over there. You will have subspace of dimension 100. So you can solve your model on a subspace of dimension 100 on a small laptop in real time. So mathematically speaking, you are projecting, is a Galerkin projection of the whole global system onto a subspace of very small dimension, which however carries a lot of information on the phenomenon, because this is made of the basis functions that are the solution of those individuals. So if you choose those individuals in a suitable way, right, if this is a good sampling, then you can expect this type of procedure to be meaningful and to produce accurate results. So we are dividing here two phases: the offline phase, where you say create this database, and the online phase, where you want to solve real time the problem. Now, I would like to conclude by mentioning that at this stage, the interplay with machine learning, artificial intelligence could be very beneficial. Now, this again is a kind of a caricature, right? A kind of cartoon. This is just to polarize the basic differences between what I call physics-based modeling, the ones that we have seen before, the ones that are based on basic physical principles, and then on partial differential equations, and data-driven models, like the ones that are say, governing the artificial neural networks, right? In the physics-based models, the a priori knowledge is predominant. You are representing that type of specific physics, the electrophysiology, the mechanics, the fluid dynamics, the valve dynamics. You use equations, and those equations are there, and they're valid in any possible context for every possible individual. You have very few data, just those that are necessary to provide you with a well-posed mathematical problem. So the lower information you have, the more data you need. And in the extreme case, you have, say, artificial neural networks that are only driven by data. So those are the two extremes, right? Now, in a different way, you can say that you have two different layers. The green one and the red one. The green one is the one based on physical knowledge, on equations. I'm sorry, this is in Italian, okay, but I think that you understand it. So this is a real problem, whatever it is, and this will allow you to develop the model, and this will be independent of the data. The model is independent of the data. Then, of course, the model will need data to produce a solution. So all the equations that you have seen before are valid for any type of heart. The data will characterize my heart rather than your heart and his heart, right? And then you produce a solution. When you use artificial neural network, basically you need data, and data representative of, say, the input and the output. And the method will learn out of those data, irrespective of the type of process that has generated those data. So there is no a priori knowledge of the context, of the physical problem that has produced those data, right? So you can see these two approaches as completely independent. Of course, with different type of potential, different type of mathematical foundation, and different type of, say, capability to reproduce specific phenomena. As a matter of fact, there is a lot of room for interplay for creating an interplay between the models. And we do it already in many different instances. For instance, if you stick with the upper layer, when we have our deterministic model, I told before that this is a multi-scale problem. We describe the problem at the level of continuum mechanics, but then we have to go to the cell level. This is where you have to account for the rheology of the material, or for the biochemical reaction, say. So we use neural networks to model what's going on at the microscopic level. And we use these two through a suitable upscaling to feed our original model. So roughly speaking, we use experiments to have a better insight or insightful knowledge of the model. This is one way, right? On the other side, very often we use the model to produce data for the neural network. If you have a good model for the heart, you can use it and to describe many different types of scenarios. You can produce synthetic data that would not be available otherwise, because having the data for the heart would mean having a very intrusive and invasive, say, intervention on different patients, which would not be possible otherwise. This is one way you can use the upper model for the lower model. There's another way. When we find solutions, we have to minimize a functional or a loss function, say. Now, the loss function typically is expressed in terms of comparison between the results that are produced by the artificial neural network and the result that you have been using for training the neural network. You can, however, enrich this functional or this function by including the residual of the physical equation that you are trying to reproduce. So the model equation. So this is a very simple case. This is a diffusion equation, right? In that specific case, you can add something that you add to your functional the discrepancy between alpha delta u, say, the diffusive term, and the time derivative of u, just to make an example. There are many different ways you can end up with this type of, say, creating a synergy between the two approaches. And my understanding is that you really need a cooperative game. The knowledge incorporated into a mathematical model is essential to make predictions outside the range of the training data set. If you are outside the range of the training data set, if you want to use artificial neural network, it's very difficult to get meaningful results. To make predictions outside the range of the training data set, to account for variation of the system when you change the rules of the game. For instance, you introduce a prosthetic device, and then you are changing completely the physiology of the system. And to account for data variability and for the fact that sometimes you have data that are not known or that are affected by errors. Okay, I'd like to conclude by this sentence. I'm quoting this paper. This paper says that models based on first principles, those that I have described before, basically those are based on partial differential equations that reflect specific physical processes, are essential components of systems that extract valuable insights from massive data. Insights that tend to go far beyond what you can be recovered by black box statistical modeling alone. Of course, it's a kind of biased view, right? But I strongly believe that this is the right time for mathematicians to play at the interface between these two approaches. And there is a lot of knowledge that you can bring to the system if you try to make advantage of the two potentials. Thank you very much.
Thank you, Alfio, for a fascinating and wide-ranging presentation. We have time maybe for a couple of questions. Anyone?
Nobody. Sorry. My remarks are obviously due to the fact that my hearing is not so good, so I might have missed something that you said. But from a sort of continuum mechanics point of view, it is not viscous because the velocities are rather slow. Or if I understand, there is no viscosity.
You are talking about the blood or the structure, or the wall structure. They are both viscous, actually. The blood is viscous. The viscosity of blood is non-negligible here. The blood is viscous, so it's Navier-Stokes equations for viscous fluids, viscous incompressible. The elastic wall is viscous indeed, is viscoelastic, but the viscosity is not accounted for here because it's, dimensionally speaking, negligible.
There are good reasons, assuming. But another thing that I find always on the continuum mechanics point of view is that you can actually decide on the domain of the arterial or the venous part of the body. Now, I would have expected that there would hardly be possible to think at this distinction between red and green or whatever, because maybe, especially in the process of exchanging oxygen, they might get into little droplets.
Okay, oh sure. All right, so I talk about not the red and the green, but say the venous blood and the arterial blood, right? The arterial blood. The venous system and the arterial system. Okay, so what you're seeing here refer only to the arterial system. We are completely neglecting the venous return in this business here. This is a model. So every time you create a model, you have to simplify. So we are completely disregarding the action of the venous. We do not simulate the venous return, but you simulate the resistance that you have at the capillary level on the arterial system. We do not account here for the exchange of CO2 and oxygen that occurs at the capillary level. Because what you are interested in here is to see what happens to the arterial circulation. You have to know that more than the 40% of the deaths in Europe are due to cardiovascular diseases. And those are typically due to the heart and the arterial system. So those are the most responsible of what's going on. This is what motivates this research, actually. Right? We are not considering the venous system. If you would consider the venous system, you should simulate the exchange of quantities at the capillary level. That we do not do here. We just use electrical circuits to model the presence of the capillary levels.
I must say, I mean, congratulations, because it's the main part of work. I just some doubts.
No, this is very pertinent. There are many other things that we disregard. For instance, we do not model the metabolic response, which is also very important, right? So if you really want to simulate what's happening in our body, you should be able to account for all possible systems acting in our body, which is out of reach today. So you make simplification, but when we disregard the part, we try to at least simulate the effect that this part that we have been neglecting has on the part that we are actually addressing.
Well, I think time is up, so if there are other questions, maybe we can ask Alfio offline, but let's thank the speaker one more time. Thank you.
Thank you.